So beginning the topic of renal physiology math begins with the concept of just how much of something is going to show up in the urine. And in order to consider that, we're going to begin talking about urinary excretion. So I like this graphic because it shows you, let me pull up my laser pointer here, it shows you in a graphic form this concept of if something is coming into the glomerulus through the afferent arteriole, through the blood vessels, and it's coming in here, it either has two choices. That something, that molecule can either continue on in the blood vessel and pass through the efferent arteriole and on its way out through the kidney in totality, or it can take another path. There's two paths. It can continue through the blood vessels, or it can get filtered and enter into the proximal tubule. Any amount of substance that is excreted in the urine, so everything that shows up in the urine has to get there in some way. And there are two ways that it could get there. In order to show up in the urine, it has to either get filtered at the glomerulus, or it can be secreted from the blood vessel directly into the nephron and kind of bypass the glomerular filtration barrier in general. So the amount of something that's excreted in urine equals what was filtered plus what was secreted. Okay, that makes sense. But you have reabsorption of some of these things going on. In fact, most of what you filter gets reabsorbed back into the body. And when that happens, you would mathematically subtract that from what shows up in the urine. So if I were to write this out, and I kind of wrote it out here in words rather than in equation format, that what gets excreted in the urine equals what gets filtered here minus what was reabsorbed back into the blood plus what gets secreted back into the nephron. Okay, so if that's your kind of basic template for determining the amount of something excreted in urine, you can write that out and you can mathematically, kind of algebraically rearrange the equation and solve for any of these four factors. So for instance, if you wanted to solve for how much of something was reabsorbed, that would be tubular reabsorption equals what was filtered minus what gets excreted plus what gets secreted. So just take a few minutes, write this down, and just start moving the variables around on either side of the equal sign in kind of an algebraic fashion, and see if you can make sure you understand and can solve for any of these four variables. In summary, if excretion happened, if a net excretion of a substance occurred, then in order for excretion to be more than filtration, this is an interesting concept now. If something gets excreted, but more of it is excreted than what was filtered, then where did all of it come from? Well, you can tell yourself just by looking at these variables. If excretion rates is bigger than filtration rate, then there must have been a secretory component contributing to that. So mull on that for a minute and make sure it makes sense before going on. So the big concept here that always keep in mind is that what goes into the kidney must come back out again. And we can write this out in terms of blood and urine. RPF here is standing for renal plasma flow of the arterial system, is what that little sub A means. In basic renal physiology, we don't really differentiate between renal plasma flow and renal blood flow. That'll become more important later on in your career in more advanced renal courses. But for now, I kind of use those terms interchangeably, even though technically they aren't truly equal to each other. So what goes in via renal blood flow must come back out of the kidney, and there's only two ways that something can leave the kidney, and that is either through the renal vein or through the ureter. And we can write this out and say that arterial input, so what comes in through the arteries, it has to equal venous output plus urine output. Simple enough. But what this means is if something enters the kidney, the entry of substance X, that must equal the exit of substance X. And if that is true, then what the concentration of that substance, or X concentration in the artery, must equal the sum of the X concentration in the vein plus the X concentration in the ureter. And if you were to rewrite that, you get this phrase over here. Arterial input equals venous output plus urine output. The next equation we need to keep in mind is something called the urine excretion rate. So I'm going to use X as this kind of unknown substance that we're going to solve for. So the urine excretion rate of X equals two things. It equals the variable U sub X and the variable V. Now, U sub X is shown here, urinary concentration of X. That's what U sub X means. This is the concentration of whatever X is in the urine at a certain volume of that urine. Now, very commonly, you would see V and you might think volume. V does not equal volume. V equals urine flow rate. Urine flow rate is the rate at which urine is produced. Now, this is generally dependent on your fluid intakes and body fluid homeostatic balance. But in general, if fluid intake is increased, urine flow will increase. If you, in general, drink a lot of water, your urine output should be increased, especially in a healthy kidney. So these are our two variables we're going to talk about here. So let's look first at urinary concentration of X. So a concentration is the amount of substance in a certain amount of volume. Now, if we look at sodium, you would usually see this as U sub Na for sodium. And an example might be 20 milliequivalents per liter. So we're getting into some volume and concentrations here. Very commonly, we use milliequivalents for ionic or electrolyte concentrations. Now, let's look at urine flow rate. So urine flow rate is a rate, but what does that rate really mean? Well, that rate is a volume of something, volume of urine, in a certain amount of time. So another rate, miles per hour, kilometers per hour. Those are rates as well. Urine flow in a certain amount of time. So something in a certain amount of time. And an example, very commonly, would be 2 milliliters per minute, meaning that you are producing 2 milliliters of urine every minute. Now, an example might be you can change these variables. You can collect in terms of minutes, you can collect in terms of hours, you can collect in terms of 24 hours or 1 day. And if you change this variable and instead of in every minute you're collecting urine, you every 2 hours are collecting urine. So if you were to rearrange this and instead of showing 2 mils per minute, you could collect 240 milliliters in 2 hours. Okay, if you were to do that, you would rearrange it to show 240 milliliters in 120 minutes, and then just kind of reduce down 2 milliliters per minute. So you can see how you can go backwards and forwards and going between hours and minutes. Now, something that is more done in a clinically applicable situation is they will collect urine every couple of hours. Somebody will come in and measure the volume that was collected. It's usually collected in like a urine pail here, which is shown in this picture. And a nurse or somebody isn't coming in every minute to measure that. You're probably voiding it and collecting it on a couple hour kind of scale. So, but the standard is to write that urine flow rate in terms of milliliters per minute. Okay. So now we have our two variables, U of X and V. Now that we have U of X and V, we can calculate urine excretion rate. Urine excretion rate is U of X times V. So that's what we have here. We have two variables. Urine excretion rate equals U times V. U is right here, 20 milliequivalents per liter, 20 milliequivalents per liter, or 1,000 milliliters. V is 2 mils per minute, 2 mils per minute. Now, you got to make sure your units are the same so that they can cancel out. You multiply and then divide, and you get a urine excretion rate of 0.4 milliequivalents per minute. Okay, so this unit of urine excretion rate can be done in milliequivalents per minute, or it can be done in terms of a 24-hour time period collection. So now that you know the urine excretion rate, we can start talking about this concept called renal clearance. So clearance means the rate at which substances are removed, aka cleared, from the blood or plasma. Renal clearance means this is the rate at which something is removed by the kidneys. And renal clearance is defined as the volume of plasma completely cleared of a substance by the kidneys per unit time. Renal clearance is the ratio of the urine excretion rate, which we just calculated on the last slide, divided by the plasma concentration or the blood concentration of that substance. Units are expressed in volume per unit time, so mils per minute, liters per day, liters per hour, etc., which means the volume of plasma or the volume of blood that was cleared of that substance every unit of time, every minute, every hour, every day. The big picture is clearance is itself a flow rate. This is not the same as urine excretion rate. Urine excretion rate is how often or the rate at which something is excreted in the urine. Clearance is the rate at which substances or something is cleared or removed from the blood. So now that you know what clearance is defined as, let's write out the equation. Renal clearance of a substance equals the concentration of that substance in the urine times the urine flow rate divided by the concentration of that substance in the blood or the plasma. So this is going to look very familiar. The numerator of this fraction here, or this ratio, is concentration of X in the urine times the urine flow rate. We just got done calculating that. That's the urinary excretion rate. So the ratio of urine excretion rate to concentration in plasma gives us clearance. This is written out down here below of C equals U times V over P. Hopefully this is something that you will memorize forever, plant it in your brain bank, and pull it out whenever somebody asks you, what is the equation for clearance? C equals U times V over P. So here is an example of how to calculate this if you're given three variables: the concentration of something in the plasma, concentration of that same something in the urine, and you're given urine flow rate. So here you're given 20 millimolars of urea in blood or plasma, 400 in the urine, and a urine flow rate of 1.44 liters per day. Keep an eye on your units. On your exam, you're going to have to be able to do these math equations, but keep an eye on these units. Be able to, without looking it up, convert from liters per day to milliliters per minute, for instance. So 1.44 liters per day, you solve that out and you get 1 mil per minute. So here's your equation, C equals U times V over P. Plug and chug your variables and you get 400 millimolars times 1 mil per minute, your urine flow rate, divided by 20. You can cross out your units that are alike and you're left with a clearance of 20 mils per minute. So rather than giving you the variables, this example is giving you kind of a word equation. So think back to high school math where you got word equations now and you got to solve them. If a substance is present in blood at a concentration of 1 mg per mil and urine at 100 mg per mils and the urine flow rate is 1 mil per minute, what is the renal clearance of this substance? Make sure that you can extract from this sentence what is the blood concentration, what is the urine concentration, and what is the urine flow rate. Insert these numbers or these values into your equation, U times V over P, cross out your similar units, and you're left with 100 mils per minute. So here's your next learning objective. Now we're going to transition into glomerular filtration rate and all the variables that go into calculating that. In order to talk about glomerular filtration rate, let's quickly define the glomerular filtrate. So this is the stuff that gets filtered at the glomerulus. The filtrate itself is that kind of fluid, what gets filtered. So glomerular filtration rate is, in order to calculate that, that is representing the volume of plasma that's filtered into every single nephron of both kidneys at the same time in a certain given amount of time. So this, you can calculate single nephron glomerular filtration rate, that's SN-GFR, but for our purposes in renal physiology, when you hear GFR, you can assume that this is the net GFR of all nephrons in both kidneys at the same time. The glomerular filtrate itself is the fluid filtered across the glomerular capillaries into Bowman's space. It should be protein-free, as you learned earlier in this lecture. It should be cell-free, and it should otherwise be similar to plasma. Therefore, that glomerular filtrate, we often will interchange for the phrase plasma ultrafiltrate. So this is the ultrafiltrate of what is crossing the glomerular filtration barrier, and it should be isoosmotic to plasma. The glomerular filtration rate is approximately about 20% of the total renal blood flow in and out of both kidneys at the same time. So now we're getting into the nuts and bolts of how to begin calculating GFR. GFR should be about 20% of renal blood flow, just as something to keep in the back of your mind. It's dependent upon the balance of Starling forces at the capillaries, and we'll come back to that in a minute. It's dependent upon something called a capillary filtration coefficient, or K sub F. K sub F is calculated as the permeability factor of the capillaries, meaning just how leaky are they, times the surface area of all the capillaries available for filtration. GFR should average about 125 milliliters per minute. That is, across an entire 24-hour day, 180 liters per day. So let's take a moment and think about that. Let's appreciate that. Your kidneys, both kidneys together, in a 24-hour period are filtering approximately 180 liters of fluid every day. Now, you're clearly not, I hope not, excreting 180 liters of urine per day. So therefore, you must be recapturing most of that. In fact, you do. You recapture about 99% of what gets filtered. But just take a moment and think about just how busy these glomeruluses are. So if you know that GFR is about 20% of renal blood flow, and then we have something called filtration fraction, which I'll talk about that in a moment. Filtration fraction is about 20% of renal blood flow or renal plasma flow. Therefore, if you're given filtration fraction of 20% and you know GFR should be an average of 125 mils per minute, that fraction is 20%, then given those values, you can back calculate what is renal blood flow, because there is a direct relationship between these three variables. Filtration fraction equals glomerular filtration rate divided by renal plasma flow. So let's think about this for a moment. Renal plasma flow is representing the amount of blood, in this case it's 625 mils per minute, entering into all of your glomeruli combined in both kidneys. It's about 625 mils per minute. It goes through and this fluid enters into the glomerular capillaries, and some of it exits out the efferent arteriole, some of it gets filtered. Filtration rate should be, in a normal functioning person, about 125 mils per minute. Okay, so you have now fluid that is entering in, some of it filters, some of it leaves, but you know that what goes in must come back out, and most of what gets filtered gets reabsorbed, because you're not excreting 180 liters of urine per day. Most of that, in fact 99% of what you filter at the glomerulus, gets reabsorbed and enters back into the bloodstream and exits via the renal vein. But some of it doesn't. Some of it goes on and gets excreted in the urine. So now you have all these variables here, you have all these numbers, and filtration fraction, the fraction of what gets filtered, is the relationship of the ratio between glomerular filtration rate and renal plasma flow. Okay, so let's put this back in here. You can, if you are given two of these three variables, you can calculate and solve for the remaining one, the one that you don't know. So in this example over here, I'm giving you 125 mils per minute is your GFR. You have a 20% filtration fraction, and I'm asking you, well, what's your renal blood flow? Well, in this case, 125 mil per minute divided by 0.2 is 625. And that's in fact what this number is here. Similarly, if you want to take 125 divided by 625, you'll get 0.2 or 20%. Okay, so you can do some fun ratios here, some examples of You can calculate what is the percentage of something that gets reabsorbed. If you are given these values, you could do 124 divided by 125, 99% reabsorption rate. Okay. So right now you might be scratching your head and a little bit confused, and that's because I'm trying to teach a little bit of the cart before the horse. So if that was a little confusing, hopefully this will help clear it up. I want to talk a little bit more about filtration fraction and what that really is. So the filtration fraction is the fraction of blood flow, so the amount of blood that enters the glomerulus, and actually the fluid that gets filtered across the glomerulus and enters into the nephron. Okay, so the fraction of blood that enters into the glomerular area and how much of that gets actually filtered. Okay. Now this value changes depending upon your ultrafiltration pressure, or the pressure that's pushing the fluid to get filtered or not, which is itself influenced by your overall blood pressure. As your filtration fraction increases, interestingly enough, the oncotic pressure of the efferent arteriole increases. And I'm asking you to consider why. And when that happens, that will help facilitate reabsorption of tubular fluid later on in the nephron. Okay, so let's think about this. This graph over here on the right, on the x-axis, is representing the distance along the glomerular capillary. So if you were to kind of draw a little picture here of a glomerular capillary, so this is your glomerular capillary. All right, so there's your glomerular capillary. The afferent end is over here, and the efferent end is on this side. So that's what this graph is indicating, the afferent end of the glomerular capillary and the efferent end of the glomerular capillary. Okay, so x-axis down here and the distance along it. The y-axis is your glomerular colloid or oncotic pressure. Now your oncotic pressure is one of those Starling forces. This is the Starling force as contributed by the presence of things like proteins. I typically will often interchange colloid for oncotic pressure, but I'm just kind of throwing those two terms up here at the same time to show you what this is really indicating. So y-axis is the oncotic pressure in the glomerular capillaries. X-axis is the distance along that capillary. So what you'll see here is this is normal filtration, normal glomerular filtration, okay, in this middle line. So at the beginning of the afferent end of the glomerular capillaries, you actually have a fairly lowish colloid oncotic pressure. But by the time you get to the end of the glomerular capillaries and you're entering the efferent arteriole, your oncotic pressure has gone up. Why is that? Well, the reason why is you have a bunch of fluid getting dumped into the beginning of the glomerular capillary, and fluid is filtering out. Stuff is leaving the blood vessel. It's crossing that glomerular basement membrane, entering into Bowman's space. But there is stuff that gets left behind, and the things that get left behind are those big things, cells and formed elements and big proteins. So proteins get left behind, but water is leaving. As water is leaving out the glomerular capillary, entering into Bowman's space, the concentration of the proteins getting left behind grows and grows and grows and grows, such that their exertion of oncotic pressure goes up by the time you get to the efferent end of the glomerular capillary. So now let's think about this. If you were to increase filtration fraction, you're increasing the amount of fluid filtering at the glomerular capillaries, then that is going to have kind of a trickle-down effect, a secondary effect on oncotic pressure, because this middle line is representing normal fluid leaving and getting filtered. If you increase the filtration fraction, more fluid than normal is leaving. Therefore, the proteins getting left behind are even more concentrated than normal. And then the opposite thing happens if you were to decrease filtration fraction. If you were to decrease the amount of fluid getting filtered at the glomerulus, not as much fluid gets left behind. Therefore, the concentration of the proteins aren't quite as much as would be normal. So this is showing you the relationship between oncotic pressure in the glomerular capillaries as it begins at the afferent end, and then by the time you get to the efferent end. And you can extrapolate, leaving the efferent end of the glomerular capillary, that turns into the efferent arteriole, which turns into what? That turns into the peritubular capillaries. So what goes on and the amount of stuff getting filtered, your filtration fraction, your glomerular filtration rate, even your glomerular blood flow, those elements that have influences, those three factors that influence filtration fraction, can influence glomerular oncotic pressure at the efferent end of the glomerular capillaries, and therefore influence oncotic pressure in the peritubular capillaries. That's what this bullet point is trying to communicate down here. As your filtration fraction changes, the efferent arterial oncotic pressure changes, and that's going to influence reabsorption of fluid from the proximal tubule. And we'll talk about that more later. So I want to make sure that this is clear before we go on, and that is filtered load is not the same as filtration fraction. Filtered load is a rate of something getting filtered per minute. Filtration fraction is the ratio of fluid getting filtered compared to total renal blood flow. So what is the basic process of urine formation? Well, to form urine, you need to have fluid getting filtered at the glomerulus, and what we call the isoosmotic ultrafiltrate. So that's going to transform into urine, and the way how is stuff is going to leave that ultrafiltrate. It's going to get reabsorbed. Some other stuff is going to get secreted back in, and together that forms what gets excreted. So if you think about kind of two things happening simultaneously, you can think about fluid getting filtered, water from the blood is filtering down. Some electrolytes are getting filtered. Some things like glucose is getting filtered. Otherwise, what remains behind in the capillary continues and flows on through its life and enters into the efferent arteriole and eventually the peritubular capillary. Some of the stuff that got filtered will get reabsorbed. Some of the stuff that passed on through the efferent arteriole and into the peritubular capillary will get secreted back in. And together, the result of these two things form what gets excreted. So let's expand that same graphic and now apply some numbers to it. So you'll see up here in the upper right hand corner, this is a very important slide. Make sure you can do all of the math we're about to talk about and understand it. Okay, so let's look at an example of net reabsorption of sodium. So let's look at sodium. So you have sodium floating in the blood. It's coming into the glomerular capillary. Fluid and consequently sodium get filtered at a certain filtration rate, and you have a certain concentration of sodium in the blood. This times this gives you your filtered load. So you can get a filtered load of sodium per day, meaning you get, in this example, 25,200 milliequivalents of sodium getting filtered, getting loaded into the proximal tubule per day. Okay. Now, some of that sodium is going to get reabsorbed. Reabsorption equals what gets filtered minus what gets excreted. Okay. So if you were to apply some numbers here, you could have that filtered 25,200 milliequivalents per day minus what gets excreted. Now, in order to solve for reabsorption, you can get the value for what is excreted by measuring stuff in the urine. So you can get numbers for how much sodium is in the blood, and you can get numbers for how much sodium is in the urine. And if you calculate the urine excretion rate of urine flow rate times the urine concentration of sodium, and you have, say for example, a 1 liter per day urine flow rate times 100 milliequivalents per liter concentration of sodium, you get a number for how much sodium gets excreted per day. And in this example, it's 100. So now you can calculate reabsorption by doing your filtered load minus your excretion. So 25,200 minus 100 gives you a reabsorption rate of 25,100 milliequivalents per day. So if I ask you an example, what is the percentage of filtered load of sodium gets reabsorbed per day? So the percentage of filtered load that gets reabsorbed per day would be how much gets reabsorbed divided by how much was filtered times 100, and you get 99.6%. So keep in mind that there are a number of variables at play in order to calculate any of these things. If you're missing one of those and you have the other variables, you can solve for them based on these relationships. Variables at play here are the glomerular filtration rate, the plasma concentration of sodium, or whatever it is you want to measure, the urine flow rate, and the urine concentration of whatever it is that you're wanting to measure. So play with these numbers, make sure you can solve for the other values given 3 of the 4 variables. So from this, you can use renal clearance to estimate GFR. Okay, there's some kind of rules behind, when you're able to do that. But in general, your amount, what gets filtered, if your filtered amount is the same as what gets excreted. So the amount filtered has to equal the amount excreted. If that is true, then you can say to yourself, well, the amount filtered is the input of something into Bowman's space equals the amount excreted, or the output into urine. Okay, so what goes into Bowman's space? That's the glomerular filtration rate times the plasma concentration of that something. What gets output into urine? Well, that's the urine excretion rate. So the urine concentration times the urine flow rate. Now, assuming glomerular filtration rate is the same as clearance, if certain conditions are met, and you can do that, GFR equals C, you can kind of substitute GFR times C there and rearrange your equation. So instead of GFR, you put a C, you get C times P equals U times V. Rearrange and you get your famous clearance equation, C equals U times V over P. Okay, meaning that if this condition is true, you can substitute GFR for C. So this is an easy way to calculate GFR under certain conditions. And those conditions are that the substance you're measuring, so all these little X's here, has to be freely filterable at the glomerulus. It can't be reabsorbed or secreted. It can't be synthesized, broken down, or otherwise accumulated or gobbled up by the kidney. And it must be physiologically inert, so it can't be a toxin, it can't change renal function. So if all of these things are true, then you can use clearance to calculate GFR. And remember, again, normal glomerular filtration rate should be hovering around 125 mils per minute. And one of the substances that meets those 4 conditions is a substance called inulin. Inulin is freely filtered at the glomerulus, but it's not reabsorbed or secreted. And the amount that appears in the urine is exactly the same as the amount filtered at the glomerulus. So what that means is you can use the values given for urine, concentration of inulin in the urine, the concentration of inulin in the plasma, and the urine flow rate, and you can rearrange this equation and solve for GFR. So this is a graphic depicting what happens to inulin. It's freely filtered, but it's not reabsorbed and it's not secreted. And what gets filtered is exactly the same that appears in the urine, and therefore you can use inulin to calculate glomerular filtration rate. Another substance that meets those qualifications or those criteria is creatinine. Creatinine, if you can recall from musculoskeletal physiology, creatinine is formed by the metabolism of creatine phosphate from muscle, so it's an endogenous compound. It is freely filtered at the glomerulus. However, creatinine concentration is pretty dependent on individual's age and the muscle mass that they have, but creatinine production is pretty close to being equal to the excretion of creatinine. So therefore, it's useful for long-term monitoring of renal function. And this graphic here times renal plasma flow entering into the glomerulus times GFR. No tubular reabsorption or secretion of creatinine occurs. And so you see nothing is moving back and forth between the peritubular capillaries and the nephron. Therefore, the amount filtered equals the amount excreted. And therefore, you can use creatinine to estimate glomerular filtration rate if you're given the other three variables. Now, in clinical situations, the GFR of a patient is usually determined by measuring the clearance of creatinine because, like inulin, it's freely filtered at the glomerulus. However, it's not perfect, okay? In contrast to inulin, a small amount actually gets secreted from the peritubular capillaries back into the nephron. And the amount of creatinine in the urine actually does include what gets secreted. Therefore, it's not a perfect marker for glomerular filtration rate. However, it is still used clinically. So despite this small error, creatinine is still used to measure GFR, one, because it is produced endogenously by skeletal muscle, and two, it doesn't require a continuous infusion. Inulin would require a continuous infusion. Therefore, it's pretty easy to do a creatinine clearance because the patient can do it at home simply by collecting their urine over a 24-hour period. And you just take one blood sample to measure plasma concentration of creatinine, and you can get kind of a GFR measurement that way.